Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over number 2 on how to graph and analyze parent trig functions. This standard is covered in pre-calculus and trigonometry. If you want to gain access to the entire playlist, the entire course, or valuable worksheets that can help you to master mathematics, just take a look at the links in the description below. So if this sounds like what you're looking for, don't forget to hit the like and subscribe buttons so you can gain access to future uploads. Alright, so the instructions for the example we are going to be working on is as follows. We are to sketch the graph of the given function on the specified domain, then describe the behavior, basically intervals where it's increasing, decreasing, find the extrema, absolute and relative extrema, the concavity where it's concave up or down, and the points of inflection, if any. Okay. Alright, so the function that we are going to be taking a look at for number 2 is y equals negative 3 cosine x on the interval negative pi and pi over 2. Alright, so let's go ahead and take a look at how to draw this graph. So we have y equals negative 3 cosine x. So this is a multiple of the parent trig function. If we can determine what our amplitudes and periods are, then it's going to be easy to draw the graph, okay? So to determine the amplitude and periods, I'm going to rewrite this function as y equals negative 3 cosine parentheses, then the coefficient of x is the invisible coefficient, which is 1 times x. Okay, writing it in this format helps us to know exactly what a and b are. So there goes your a value right there, negative 3, and then your b value is 1. Okay, so let's find the amplitude and period. So for the amplitude first, for the amplitude, we're going to use the formula absolute value of a. Okay, so the absolute value of a in this case is absolute value of negative 3, which is 3. So what does this mean? You go 3 units from the center to the maximum and 3 units from the center to the min. Okay, that's the maximum displacement from the central position. And then for the period, we're going to use the formula 2 pi divided by the absolute value of b. Okay, in this case, it's going to be 2 pi divided by the absolute value of 1, which is 2 pi over 1, which is 2 pi. Okay, this helps us to calibrate our x-axis. It tells us that 4 ticks will give us 2 pi, which represents 1 complete period or cycle. Alright, now we have all the information that we need to sketch our graph. So let's go ahead and draw our coordinate system. So we'll start with our y-axis. So there goes our y-axis right there. And then our x-axis. Alright, so let's go ahead and calibrate the x-axis first. So we remember what our period was. 4 tick marks is equal to 2 pi. So we have, see, this is a first tick mark. This is pi over 2, or the first quarter of a full circle, which is 90 degrees, pi over 2, pi or 180 degrees, which is half of a complete period, pi or 180, and then we have 3 pi over 2, 3/4 of a circle, or 270 degrees, and this is 2 pi. This is a complete cycle. Okay, for this graph, we are not going all the way to 2 pi. I just wanted to illustrate to you what 4 ticks equals 2 pi means. We're just going to be stopping at pi, alright? And then going in the negative direction, we're rotating clockwise now, okay? So our angles will be negative. So if you go 1/4 of a circle in the clockwise rotational direction is negative pi over 2, or negative 90 degrees. And another 1/4 of a circle will take you half of a circle, half of a complete period, which is negative pi. We can stop right there because that's the left endpoint. Okay, so there goes the calibration for the x-axis. Now let's take a look at the calibration for our y-axis. For y-axis, notice the amplitude is 3, right? So the maximum displacement from the central position is going to be 3. Alright, remember in the previous presentation in part 1, our amplitude was 1, I think, and we just put 1 here and then negative 1 down there. Alright, so there goes the maximum, 3, and then the minimum is going to be negative 3. Alright, so there goes our maximum and minimum displacement from the central position. So what we're going to do now is give ourselves a visual so that we do not exceed the limits of this function. Okay, so let's give ourselves the visual constraint as to what the maximum is. So that's the highest point that the graph is going to go to, and then the minimum is negative 3. So the graph doesn't go below this and it doesn't go above that. Okay. Alright, so we have our graphs calibrated. We've also included our boundaries, our boundary lines for our max and min. Now we're going to proceed to draw the graph. Okay, so what does the negative cosine function look like? So we went over this in the previous presentation, but we're just going to go over that again just to reinforce the process. And that is our guide as to what the general look of the sine and cosine functions are, including their opposites. So for the sine function, this looks like what? S for sine. The sine function, the positive sine function, looks like an S, right? So something like that. Alright, so there's the positive sine function. That's a complete period. A complete period for the sine function looks like an S, and in the other direction goes something like that. Okay, let me sketch it properly. Alright, so this is a general look of the positive sine function. Okay, center, max, center, min, center. So just remember that your sine function looks like an S. That's what it looks like. Okay, how about your cosine function? Your cosine function, C for cosine, looks like what? Do you remember what we talked about in the previous presentation? The cosine function looks like a cup. Okay, so sine starts from the center, cosine starts from the top, and then it has this cup-like look. Alright, so that goes a complete period for your cosine function. The cosine function looks like a cup, like that. That's one period. This is a complete period to the right, and then to the left, that also looks like a cup too. That's a complete period to the left. So just knowing what the general look of a trig function is can really help you to configure your points. Alright, so these are the positives. Now what about the negatives? What if I wanted to graph negative sine? What does that look like? Now A is negative. What kind of transformational effect does the negation of A have? It causes a reflection across the x-axis. So negative sine will be this regular sign reflected across the x-axis. So it's going to look like a sign that has been flipped. Alright, so this is what your negative sine function will look like. Alrighty, so to the right and then to the left, it's just a general sketch as to what it looks like. Looks something like that. Now how about your negative cosine function? The same effect, right? You have your cup that has been flipped upside down. Okay, so you look at this cosine we have here, we're just going to flip it upside down. So instead of starting from the max, we're going to start from the min, and that cup right there, that is a complete period of the cosine function. Alright, to the right and then to the left, exactly the same thing. Alright, so these are the configurations of the sine and cosine functions. For this particular example, we're graphing negative cosine, so our graph will be looking something like this one right here. Okay? Alright, so let's go ahead and graph. Now when you're graphing your points, you always want to start orienting your points relative to the y-axis. Alright, so for the negative cosine, what we're going to be doing is we're going to be starting from the minimum position on the y-axis, and then we'll graph our points. We're going to graph our points for the upside down cup. Okay, so going to the right, one tick mark takes you to pi over 2. Now if you notice that right here is a bracket, so another way to write this interval notation, we can write it using an inequality, which is negative pi is less than or equal to x and is less than, sorry, let's fix that. Negative pi is less than x, and x is less than or equal to pi over 2. Okay, so this is an open circle and this is a closed circle. Alright, so on the left endpoint we have an open circle. On the right endpoint it will be a closed circle, which basically indicates that the left endpoint is excluded and the right endpoint is included in the graph. So pi over 2 will be a closed circle because we have a bracket here, which is a closed circle. Okay, now let's go ahead and graph our points to the left direction, now rotating clockwise from the min to the center, and then from the center to the maximum. Now the left endpoint is parenthesis, so we have to exclude negative pi. So we illustrate that using an open circle. Alright, so let's go ahead and connect the dots to graph our function y equals negative 3 cosine x on the specified domain. So when you're underneath the x-axis, is going to have an upward facing concavity, and way above is concave down. Alright, so concave up to the center right there, and this is concave up to the minimum, and then this is concave down to the central position right there. Let's do that again. So this is concave down. Alright, so there goes our cosine curve. Okay, so now that we're done with the graph, we're now going to carry out our analysis. We're going to look at the properties of this graph right here. We're going to start off by taking a look at the behavior. Okay, so let's write down analysis. We're going to look at the behavior. So for the behavior, what we're looking for is where the graph is increasing and where it's decreasing. Okay, so where is the graph increasing? The graph is increasing where the function is going up from left to right. Okay, so look at the graph. Where is it going up from left to right? We can see that it's going up from left to right from 0 all the way to pi over 2. So let's mark that on the graph. So from here it's going up, up, up. It's increasing, increasing, all the way to this point right here. So let's specify what that is. So it's increasing from, we're going to exclude 0 because right here is neither increasing nor decreasing, all the way to pi over 2. So right at that point, right at pi over 2, it's an interior point and the direction hasn't changed yet. So we expect it to keep increasing. So pi over 2 is included in the increasing interval. Alrighty? So that's the only interval where it's increasing. Now where is it decreasing? The function is decreasing on the interval of the graph where the graph is going down from left to right. So do you see where the graph is going down from left to right? Yes, from pi over 2 all the way to 0. Alright, so let's indicate that. So the graph is going down, 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 down. It's decreasing, 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 going down, decreasing from left to right all the way to 0. Okay? So our interval where the graph is decreasing is from negative pi all the way to 0. Okay. Now let's take a look at the next set of properties, basically the extrema, max and min, absolute, and relative. Alright, let's start with the relative maximum. Okay. So the relative maximum are your peaks or the endpoints that you're ascending to or descending from. Okay, so take a look at this graph right here. This represents, so we're looking for maximum. This endpoint right here is a relative max. Do you know why this is a relative max? It is because it is an endpoint that you're ascending to. You're increasing up to that point right there. That's a relative max. Okay, now this point right here should be a relative max also because you're descending from. Okay, so if you're ascending to a point or descending from a point is a max. But why are we going to exclude this? We're going to exclude this point because it's an open circle. Pi over 2 is excluded from the domain. Alrighty. So we have just one relative max. So our relative max in this problem is y equals 0, and it happens at x equals pi over 2. That goes our relative max. Alright, how about our relative min? Our relative min are all the valleys or the low points or the endpoints that you are ascending from or descending to. Okay? Alright, so these two endpoints are maximas, so we don't even look at that. But look at this interior point right here. This is a valley. This is a low point, so it qualifies as a relative minimum. Alright, that's the only minima that we have here, relative minima. So the relative minimum is y equals -3, okay, because that's what the value is. Remember, we put -3 here before, and it happens when x is what? When x is 0. Okay, so there goes our relative extrema. Next thing we need to find are our absolutes. Let's start with our absolute maximum. So our absolute maximum is the highest of all the relative maximas that we have, okay? So if you take a look at this, this is a relative max, and this one would have been a relative max, but it was taken out. So what is the absolute maximum in this particular case? Now we have two of them here. This is excluded, but this one is higher than this point right here, and this is not defined. Okay? So what's our relative absolute maximum going to be? In this particular case, we have no absolute maximum. There are none. Why? Well, it is because the absolute maximum which we should have had is undefined. So there are infinite number of points that are arbitrarily close to this absolute maximum. No matter how close you get to this undefined point, you can always find another value that's bigger than the previous value but is less than this absolute maximum. Okay? So when a potential absolute maximum is taken out, in most cases you do not have any absolute maximum in the entire domain because of a situation where you can get infinitely close to that absolute maximum. Okay? So we have none here, because if you think about, there are other points in this region that are higher than this. So you can clearly see why this guy right here doesn't qualify as the absolute maximum. Okay? Now how about the absolute minimum? Well, look at this. This valley is defined. Had it been that this valley were an open circle, had it been that it were excluded from the domain, we'll run into exactly the same problem with the absolute maximum, and there'll be none. But since it's a closed circle and it's included in the domain, that relative min is also an absolute min. Alright, so our absolute minimum is going to be y equals -3, and it happens when x is equal to 0. Okay? Alright, let's go ahead and take a look at the concavity of the graph. Where's the graph concave up, and where is the graph concave down? So for concavity, we want to think about u's. Okay, when is our u facing up or our u facing down? Let's talk about concave up first. So we went over this in the previous presentation. We're just going to go over it again. So for concave up, let's represent that with the notation CU. Concave up is a scenario where your u is open upwards. Okay, it's like an umbrella. Nope, that's not an umbrella. That's a dish. It's like a satellite dish. Okay, so if a u opens up, that's concave up. It could be a complete u, or any part of this u will qualify as an upward opening or facing concavity, like just a partial u opening up like this. See how it opens upwards like a dish, or another u. If it opens up just like a dish, that's an upward facing concavity. Okay, so in this graph, where is it concave up? Where do you have a u facing upwards? From -pi/2 to pi/2. See how it looks like a bowl, a dish, right? So it's on this interval. Let's specify what a concavity is. It's concave up, all the way, concave up. Right here is concave up, all the way to pi/2. Okay? Alright, so let's specify that using interval notation. So it's concave up from from negative pi over 2 all the way to pi over 2. Alright, let's put that in there. So it's concave up from negative pi over 2 all the way to pi over 2. Now how about your downward opening concavity? Where is the graph concave down? The graph is concave down where you have a U that is either facing down, a whole U facing down, or a partial U facing down. Okay, so let's see what that looks like. So concave down is like an umbrella, right? You have a whole U facing down, or any part of this U that's downward facing qualifies as a downward opening concavity. So see how this is concave downwards right there, and this out right here. See how the concavity is downwards? So that's what concave down looks like. Now take a look at the graph right here. Do you see any intervals where the curvature, the concavity, is facing down? Clearly from negative pi to negative pi over 2, the concavity is downwards. So let's specify that on the graph. So here is concave down, concave down, concave down, concave down, all the way to negative pi over 2. Okay? So let's specify what that is. We're concave down from negative pi all the way to negative pi over 2. Alrighty, so that's how you find the intervals of concavity for a trig function. Now the next thing we're going to look at, lastly, are our point or points of inflection. Okay, so points of inflection are basically the points on the graph where the concavity changes. Alrighty, so take a look at the graph for a second. Do you see any points where there is a switch in the concavity? Absolutely. At negative pi over 2, at this point right here, you notice that it changes from concave down to concave up. So we have a point of inflection. Okay, so let's go ahead and write it down. Our point of inflection occurs at x equals what? X equals negative pi over 2. Alright, so that's that. Thanks so much for taking the time to watch this presentation. Really appreciate it. If you found the contents of this tutorial helpful in your studies of graphs of trig functions, do give us a thumbs up. Your positive feedback is very valuable to us. Don't forget to subscribe to our channel for updates to other cool presentations such as this. If you have any questions, comments, requests, just post it in the comment section below, and we'll be more than glad to respond. Don't forget to check out our website, mathgotserved.com, for tons of resources to help you in your studies of mathematics. Thanks again for watching, and have a wonderful day. Goodbye.